When ancient humans mastered fire, invented the wheel, and launched a raft, they did more than create new models of transportation. They laid the groundwork for engineering evolution. Since then, transportation has become the heartbeat of civilization, the industrial pulse, the technological force that determines the course of history. Speed, freedom of movement, and the expansion of borders have shaped humanity. The Silk Road facilitated not only the exchange of goods, but also the sharing of ideas, transforming the worldviews of entire cultures. The ships of the Age of Discovery connected continents, forging a new global order. 19th century steam locomotives accelerated life space, while 20th century aviation turned time into a strategic asset, effectively erasing borders and creating a world without limits. For millennia, transportation has been the engine of progress. Yet today, this once effective mechanism is failing. Roads, once symbols of freedom, have morphed into traps. Will our transportation heart continue to beat, or it is on the verge of stopping? Traffic congestion suffocates cities, exhaust fumes poison the air, and the relentless expansion of transport and logistics infrastructure threatens our natural environment. Transport, which was designed to serve humanity, has become a peril to our civilization. Every day, millions of people find themselves held hostage by transport chaos. Each year, transportation claims over 1 million lives. And every decade, we destroy more land for roads, parking lots, and bridges. In the past 25 years alone, more than 3 million square kilometers of untouched nature have vanished, an area comparable to the European part of Russia. Currently, transportation is not a catalyst for development, but a system draining our shared civilizational home, the biosphere of Earth. The paradox of our time is that we strive for development while relying on technologies that undermine its very foundation. We believe that forward motion equates to progress, yet it leads us into an ecological crisis and a dead end. The future hinges on the decisions we make today. Transportation must undergo significant transformation in the coming years. The time for contemplation has passed. Within the next 20 to 30 years, we will reach a point of no return. By 2040, the number of cars is projected to double, bringing chaos, resource depletion, and environmental degradation. We could continue to expand roads and construct new interchanges, but that would merely prop up an exhausted system. It is time to ask ourselves, what should the transportation of the future look like to ensure it preserves rather than destroys? The answer is clear. We must develop a new model of transportation, a second-level transport system that is efficient, environmentally friendly, and accessible to all nations. This is not just a new transport system. It represents a new philosophy. a conscious commitment to the future and care for generations to come. The future lies in integrated elevated transport systems that harmonize the laws of physics with modern technology. This approach is not merely an improvement of existing solutions. It is a fundamentally new paradigm for mobility. The core issue with contemporary transport is not solely its carbon footprint, but the carcinogenic emissions produced by burning dirty fuels containing sulfur and heavy metals, and not just in pure oxygen, but in air laden with nitrogen and the entire periodic table. Complete electrification of transport will not resolve this issue. It merely redistributes emissions, thereby increasing the environmental burden on power plants, where the combustion of primary energy resources continues. Simultaneously, traditional methods of constructing roads and transport hubs result in extensive land seizures, destruction of natural landscapes, and disruption of surface and groundwater flows. Thus, it is essential not only to replace one fuel with another, but to drastically reduce energy consumption and fundamentally transform transport infrastructure to minimize its detrimental impacts on the biosphere. The truly viable solution lies in developing energy-efficient, low-cost, and safe transportation systems that consume less energy, regardless of their type or source. The quest for the optimal transportation system has transcended mere technical considerations, evolving into a strategic imperative for civilization. The transportation of the future is not simply a modernization of existing technologies. It requires a fundamental rethinking that incorporates physical laws and environmental necessities. The evolution of engineering thought is gravitating towards minimal resource consumption, paired with maximum efficiency, making these innovations not only advisable but imperative. The principles of designing ideal transportation, particularly high-speed systems, hinge on several key factors. First, there is the electric drive. This technology is not only environmentally friendly, but also offers maximum efficiency in energy consumption. Second, there is the wheeled propulsion combined with rail systems. This configuration minimizes energy loss due to rolling friction. The choice of steel as the primary contact material for wheels and rails ensures durability and reliability. Third, the aerodynamic design of the vehicle's body plays a critical role in reducing energy costs. By eliminating protruding elements, such as wings, rudders, and chassis, we significantly minimize air resistance. At speeds exceeding 100 meters per second, over 90% of energy consumed is dedicated to overcoming aerodynamic drag. The fourth point is the abandonment of solid road surfaces. Modern technologies enable transport systems to be elevated to heights of 5 meters or more above land or water. This innovation not only mitigates environmental impacts, but also addresses traditional issues like traffic congestion, extensive land acquisition, and accidents. Last but not least element of high-tech transport is the string rail. This innovative approach utilizes a pre-stress structure for the track, enhancing safety and energy efficiency. The combination of these components opens up new horizons for transport systems, enabling safe, energy-efficient, and environmentally friendly transportation. For progress to be meaningful, it must extend beyond developed nations. The socio-economic feasibility of innovations at a global scale is important. Transportation must be accessible to all countries, particularly given the limited budgets and infrastructure challenges faced by developing regions. For context, the cost of constructing a traditional elevated metro system in the United Arab Emirates exceeds $100 million per kilometer, while a ground tram can cost as much as $85 million. Such figures are often prohibitive for many countries in Asia, Africa and Latin America, where there is a pressing need for efficient yet economically viable infrastructure. The world requires elevated systems that can be built for no more than $4 to $5 million per kilometer, comparable to the cost of an asphalt road. This approach allows for the development of transport without the exorbitant costs and material-intensive structures that characterize traditional elevated systems. Today, advanced transport complexes that meet all criteria for clean transport are not just visions of the future. They are operational realities. A clear indication of this is the successful operation of 7 test UST complexes, passenger, cargo and mixed use, that have been functioning since 2015 at Eco Technopark in Belarus and since 2018 at the UST Testing and Certification Center in the United Arab Emirates. And since 2024, Belarus has become the site for the first commercial UST project, the U-Light tourist route, which embodies the ideas of affordable, environmentally friendly and efficient transport. The UST technology employs a string rail overpass, ensuring reliability, safety and low material consumption. This allows for passenger and cargo transportation in urban areas at speeds of up to 150 km per hour, and between regions, countries and continents at speeds approaching 500 km per hour. Future developments even envision speeds of up to 1,200 km per hour in 4 vacuum tunnels. The string rail track structure avoids the undesirable airfoil effect seen in other systems. Constructed with pre-stressed string elements made from steel, basalt fibers or carbon fiber, it boasts exceptional durability and resistance to external influences. Additionally, the minimal earthworks required and the reduced land acquisition area make it the most environmentally friendly solution among elevated transport systems. In contrast to magnetic levitation, maglev systems, UST vehicles, unmanned rail electric vehicles on steel wheels or U-pods, offer maximum efficiency. The electric motor wheel achieves efficiencies exceeding 90%, while the efficiency of a linear electric motor in a maglev train typically does not surpass 50%. The UST complex can be configured as a monorail, bi-rail or quad-rail system, with options for either mounted or suspended designs, allowing for adaptation to a wide range of specific tasks. Depending on project requirements, the track structure can be designed to be flexible, semi-flexible, semi-rigid or rigid, with span lengths capable of exceeding 3,000 meters. Thus, the UST implements a comprehensive approach, integrating the finest engineering principles, from mechanics and aerodynamics to electrodynamics. The energy efficiency of any transport system determines its economic and environmental viability. Physics reveals a surprising fact. The efficiency of a ground-based transport system located at the bottom of the planet's flat gravitational well is effectively zero. This is because all of the energy expended on movement, 100% of it, is not used for useful work when the vehicle moves horizontally, but rather to combat environmental factors: heating the air, wheels, road surface, exhaust gases, noise, vibrations, and wear and tear on all moving parts. Each cycle of vehicle acceleration incurs significant energy costs, while braking converts accumulated energy into heat and mechanical wear. This problem is particularly acute in public transport, where multi-ton vehicles often carry only a few passengers during off-peak hours, consuming most of their energy not for moving cargo, but for themselves. But what if these forces of nature began to work for transport? Gravity is a powerful tool, capable of transforming movement into energy efficiency. In elevator systems such as UST, acceleration can occur naturally on specially designed descents, and braking can happen through a subsequent smooth rise in the track structure. This technology enables urban transport to accelerate and stop in a natural cyclical motion mode, eliminating energy losses. Gravity becomes the engine of the future, providing maximum mobility at minimum cost. Energy will not be wasted in the air. It will be converted and conserved. Transitioning to these principles means a departure from conventional energy-extensive acceleration and braking methods, which will lead to reduced wear and tear and significant economic effects. This concept is based on a gravitational recuperator, a mechanism that enables the conversion of potential energy into kinetic energy with 100% efficiency and no losses. In elevated transport systems like UST, such a solution becomes technically feasible, as it is possible to design a height difference between adjacent stations using natural physical processes. On inclined sections of the track, the U-part first accelerates under the influence of gravity, reaching maximum speed without additional energy consumption. As it approaches the station, its trajectory rises, enabling natural deceleration without the need for active braking. With proper trajectory design, the elevation difference between stations enables movement without the need for energies or brakes, significantly reducing energy consumption and minimizing wear on brake pads and wheels. For instance, on a kilometer-long section of track featuring a sagging design and a height difference of 25 meters, the U-part can reach a maximum speed of 80 km per hour without energy loss. The average speed would be around 60 km per hour, 1.5 times faster than the Moscow metro. In the same kilometer-long stretch, the sagging-type UST demonstrates a remarkable 12-fold reduction in energy consumption compared to a one-sided inclined straight-track structure. When compared with traditional urban transport options, such as buses, subways, and trams, UST with a horizontally aligned track structure reduces energy consumption by 3 to 5 times. Furthermore, implementing a long-span suspended sagging-type overpass based on principles of gravitational acceleration and deceleration can cut energy usage by nearly 100 times. The suspended track structure eliminates 10 to 20 supporting towers per kilometer, leading to reduced material use and lower construction costs. In urban settings, sagging-type USTs can operate atop high-rise buildings, entirely removing the need for costly land allocation for transport and logistics infrastructure. To offset energy losses during operation, the U-Pod necessitates a height difference of 2 meters per kilometer of track, enabling it to traverse 1 kilometer in approximately 60 seconds. Increasing the sag of the track structure can further enhance speed and decrease travel times. Let's engage in a thought experiment to explore the advantages of the suspended UST sagging type compared to magnetic levitation trains, which many experts tout as the future of transport. Imagine a linear city stretching 9,000 kilometers from Moscow to Vladivostok, with exactly 1 kilometer between clusters, each featuring a stop. The terrain is perfectly flat. One route is horizontal for the maglev train, while the other incorporates a sagging design with 20-meter deflections over each kilometer. In both scenarios, we assume ideal magnetic cushioning, which the U-Pod can also utilize, and ideal aerodynamics for the rail electric vehicle, with no energy losses. Electric vehicles weighing 20 tons, similar to trams, are set in motion at a snail's pace or just 1 millimeter per second. Now we wait for the results. The outcome? The maglev train would take an astonishing 285 years to reach Vladivostok. In contrast, the suspended UST would complete the journey in just 6 days and 14 hours. Moreover, by increasing the sag, the average speed could rise, potentially reducing travel time to 4 to 5 days, even at the initial speed of 1 millimeter per second. While such an experiment is impractical in real-world logistics, it starkly illustrates the primary advantage of the UST. Gravitational energy is effectively converted into speed. This sagging structure not only enhances transport speed, but also boosts energy efficiency. While traditional systems remain tethered to horizontal designs, UST leverages nature itself, creating a transformative new reality for urban mobility, with a track structure that sags under its own weight. Modern megacities have strayed from their primary purpose of being convenient for people. Instead, they have transformed into dense hubs of car traffic, where infrastructure prioritizes vehicles over residents. Each year, over 60 million new cars are added to the global fleet, exacerbating traffic congestion, noise, and pollution. Asphalt has replaced ecosystems, and concrete has buried fertile land. Cities expand at the expense of the biosphere. For instance, Chongqing in China, the world's largest metropolis, is now equal to the size of Austria. Linear U-cities represent not just an alternative to megacities, but a revolution in urban planning. These cities consist of a chain of pedestrian clusters connected by a sagging-type UST track structure, eliminating traffic jams, exhaust fumes, and congested roads. Nearby, passenger and freight rail systems, along with the high-speed UNET transport corridor, will facilitate intercity, continental, and intercontinental travel. Residential cluster represents not a concrete jungle, but a settlement harmoniously integrated into any natural environment, with low-rise buildings, rooftop greenhouses, and pedestrian streets. Essential amenities, offices, shops, medical centers, and recreational spaces will be within walking distance. Agriculture will operate in a closed cycle. producing U-Terra biohumus, the elixir of fertility. This will enable the city not only to provide organic food, but also to create fertile soil in previously inhospitable areas, deserts, mountains, and offshore platforms. Industrial clusters will be strategically located to preserve the ecological integrity of urban environments. Each cluster will function as an autonomous ecosystem supplied with clean bioenergy, organic food, and spring water. With a population density of approximately 2,500 people per kilometer of linear city, this system could comfortably accommodate 10 billion people, occupying just 1/37th of the Earth's landmass. The remaining space would be dedicated to nature, forests, meadows, reserves, and national parks. Today, we stand at the threshold of a new era, the era of geospace expansion. Humanity will inevitably reach beyond our planet, transporting industrial technologies into space. However, we first need to reconsider our relationship with our cradle, Earth. The EcoSpace program proposes innovative solutions: a general planetary vehicle and the industrial space necklace, Orbit, designed to facilitate large-scale movement of cargo and passengers between Earth and near space. A central element of this initiative will be the Equatorial Linear City, an unprecedented infrastructure project spanning 40,000 kilometers. This city will serve as a fundamental transport and infrastructure complex for geospace logistics, personnel training, assembly of space structures, and management of space flights. The city's central axis will feature the GPV takeoff and landing overpass, integrating advanced UST transport technologies, autonomous energy systems, and scientific and industrial clusters. By embracing this approach, humanity can develop without compromising Earth's ecosystems, preserving and enhancing natural resources. Linear cities are not merely a transportation and architectural revolution. They represent a new path for civilizational development, where technology supports nature rather than undermines it. This will serve as an alternative to the unpromising colonization of Mars proposed by some visionaries. Why venture to a desolate planet when we can cultivate our shared home, Earth, into a flourishing garden? Rather than surviving in inhospitable extraterrestrial conditions, humanity can build a harmonious future right here on Earth. The future of space logistics may be a topic of extensive debate, but one constant remains: all technology adheres to the fundamental laws of physics. These laws dictate how every mode of transport operates, whether bicycles, cars, airplanes, or rockets. Anatoli Unitsky is not proposing a utopia. He is designing a system that aligns with key physical criteria of efficiency, safety, and environmental sustainability. The GPV is a self-supporting geospatial aircraft capable of launching millions of tons of cargo and passengers into space without relying on chemical jet engines. There are no bulky launch pads or atmospheric pollutants, nor are there destructive shock overloads. Instead, the focus is on precise engineering calculations, the exclusive use of electrical energy, and its maximum recovery. Imagine a colossal ring encircling the Earth at the equator. Within this ring, ribbon flywheels are accelerated by linear electric motors to cosmic speeds of approximately 10 kilometers per second. Centrifugal force generates lift, enabling cargo and passengers to be transported to orbit and back with maximum energy efficiency. The acceleration and deceleration are smooth and comfortable, ensuring a ride as gentle as the finest railways, free from shaking or overload. Technically speaking, the GPV functions as a giant three-wheeled U-pod. One wheel comprises the body carrying passengers and cargo, while the other two consist of ribbon flywheels, each with a starting diameter equal to that of the Earth, 12,756 kilometers. Modern launch vehicles represent significant technical achievements, yet they inflict substantial damage on the Earth's ecology. Emissions of high-temperature toxic plasma, destruction of the ozone layer, and exorbitant costs associated with transporting each ton of cargo render space travel a privilege for the few. The GPV offers a transformative alternative, affordable and widespread access to orbit, where ticket prices rival those of high-speed train journeys. Geospace logistics will become an integral part of the global transport system, rather than an exclusive endeavor for the elite. The cost of delivering a ton of cargo could decrease by thousands of times, falling below $1,000 per ton. Space will no longer be an unreachable frontier. It will become a natural extension of Earth's transport arteries, linking cities, countries, and continents. The General Planetary Vehicle is not merely a concept. It is an engineering project grounded in decades of calculations and research. Ideas once viewed as futuristic dreams are now emerging as viable technological solutions. History demonstrates that the most ambitious concepts often seem impossible at first, only to evolve into everyday realities. As humanity embarks on its ambitious journey into space, the need for new infrastructure to support living and working beyond Earth becomes increasingly urgent. Rather than scattering objects throughout space, it is far more logical to integrate them into a unified transport and industrial system. This idea led to the conception of the Industrial Space Necklace orbit, an orbital complex encircling the Earth in the equatorial plane at an altitude of approximately 400 kilometers. By positioning the space industry as close to the Earth's surface as possible, geospace logistics are simplified, making cargo transportation both cost-effective and efficient. This innovative approach transforms orbit into a convenient hub for production, research, and extraterrestrial recreation. Within this orbital framework, factories, laboratories, power plants, and residential modules will support the operations of space enterprises. Crucially, this environment will remain populated. While automation plays a vital role, humans will remain the heart of the industrial necklace. Technologists, researchers, workers, engineers, and tourists will find unique opportunities for work and life in conditions akin to Earth's subtropics, and in some respects even better. The UST technology stands as the only concept capable of addressing the challenges of our time. It offers a clean, energy-efficient, and safe transportation system on a second level, alleviating urban congestion, reducing costs, and tackling global logistics issues. However, its true potential extends beyond Earth. This global transportation vehicle acts as a bridge between Earth's civilization and the space industry, making orbital transportation accessible to the masses. If humanity aspires to extend the boundaries of its existence, it must develop new transportation systems. The UST solution is uniquely positioned to build industrial infrastructure beyond Earth, ranging from string railroads on other planets and the Moon to orbital transport networks in Earth's equatorial space. String technologies are not merely transportation methods. They are essential for humanity's survival in a new world, where accessing resources and interplanetary travel will become as routine as air travel. The history of civilization is defined by challenges where humanity either embraces them or faces decline. Today, we confront perhaps our most ambitious challenge: the necessity to reconstruct the planet's transportation system while exploring space without jeopardizing Earth's biosphere. Accepting this challenge means securing a sustainable future not just for ourselves, but for the entire planetary ecosystem. String technologies represent not just an alternative, but the only logical progression in the evolution of Earth's industrial civilization. The pressing question is no longer whether this is possible. It is when humanity will have the courage to take this decisive step.